Welcome to Lecture 10. In this lecture, we will focus on the Middle Paleozoic, the evolution of vertebrates, and the Devonian mass extinction. During the Silurian, Laurentia, which is North America, and Baltica, which is Scandinavia, collided along a convergent plate boundary to form the larger continent of Laurasia. This collision closed the northern Iapetus Ocean and is marked by the Taconic orogeny, the first of the orogenic events to build the Appalachian Mountains. In this illustration of the paleogeography of the Middle Silurian period, you can see the locations of Laurentia, Baltica, and the Taconic and Caledonian highlands separated by the Iapetus Ocean. The closing of the northern Iapetus Ocean resulted in the formation of the Taconic orogeny. The closing of the southern Iapetus Ocean resulted in the second round of mountain building along the Appalachian Mobile Belt, the Acadian orogeny. In the west, along the Cordilleran Mobile Belt, we have the Antler orogeny occurring, and in the north, the Ellesmere orogeny. What is important to notice in this paleogeographic map of the Earth in the late Devonian is the sea level drop on the Laurasian craton. Also notice the light blue areas. These are areas of shallow seas, habitats that would support reefs. There is also no ice at the South Pole. Here you can see the major events occurring on the North American continent. We are now in the Kaskaskia sequence with the Acadian orogeny on the Appalachian Mobile Belt and the Antler orogeny on the Cordilleran Mobile Belt. During the Devonian period, the Earth had a uniform global climate. The evidence for this exists in similar floras or plants throughout the world, the distribution of reefs in the oceans, evaporites, and red beds. The Middle Devonian marks the end of the Tippecanoe sequence and the start of the Kaskaskia sequence. The boundary between the two is of course marked by a major craton-wide unconformity. The Kaskaskia sequence ranged from the mid-Devonian to the end of the Mississippian. The Kaskaskia transgression covered the low-relief landscape of the craton, and the majority of the basal beds deposited again consisted of clean, well-sorted sandstones. If you compare the basal beds of each of the first three cratonic sequences, the Sauk, the Tippecanoe, and the Kaskaskia, you should notice that they are all clean, well-sorted quartz sandstones laid down during transgressions. These sandstones can be used to map the shorelines on the North American continent. As we previously discussed, the Devonian period is characterized by a relatively stable, worldwide, mild to tropical climate. The period is also known for large reef formations in shallow seas as the Kaskaskia Sea began to transgress into Western Canada. These reefs have been intensively studied at outcrops and in the subsurface because they contain large reserves of petroleum. These large petroleum reserves also reflect the abundance of life in the seas at this time. This map shows the location of North America during the Middle Devonian. Notice first the location of the continents straddling the equator, so we are still in a tropical and subtropical environment. Next, notice the extent of the Kaskaskia Sea over the craton. Lastly, the location of the Williston Basin in Western Canada is significant. This basin has multiple reefs in close proximity that restrict the flow of water into the basin and allow for formation of evaporites in the center. The location of the basin is also near the 30° north latitude, where evaporation exceeds precipitation. By the end of the Middle Devonian, the reefs of Western Canada had coalesced into a large barrier reef system, restricting the flow of oceanic water into the back reef platform and creating conditions for evaporite precipitation. In this back reef area, up to 300 meters of evaporites precipitated, much the same way as in the Michigan Basin during the Silurian period. This illustration shows how the formation of barrier reefs in Western Canada created a barrier that restricted fresh marine water flow into the back reef area and thereby controlled the regional facies, another case of life controlling the geosphere. The sedimentation of the Middle Devonian was primarily carbonate and evaporite deposits. That makes the change in sedimentation to black shales very conspicuous. These shales were widespread over the craton, and they ranged from the late Devonian to lower or early Mississippian periods. They were non-calcareous shales, meaning they were from terrigenous or continental origins. They were thinly bedded and less than 10 meters thick. The map at the top shows the extent of these black shale deposits across North America. Notice there is a heavy concentration of them in the east, southwest, and north. The photo below is an outcrop of Devonian black shale. The rock appears light gray in color due to weathering, but the fresh rock is a much darker gray to black. When geologists find shales of this color, they usually indicate high organic content and/or low oxygen content. This is the map we looked at previously of the late Devonian. Notice the locations of the mountain ranges. If you compare these locations to the locations of the black shales, they correlate. Remember that mountain building leads to weathering and erosion of continental sediments. It is probable that the Acadian antler and Ellesmere orogenies led to the sedimentation that created these black shales. Because most of these black shales lack large body fossils, they are difficult to date and correlate. This is where microfossils are needed, especially conodonts, acritarchs, and plant spores. These microfossils have allowed us to date the beds as late Devonian and the upper beds as early Mississippian in age. The essential features required to produce these black shales are undisturbed anoxic bottom water, a reduced supply of coarser detrital sediment like sand, and high organic productivity in the overlying oxygenated surface waters. When you have high productivity in surface water, this leads to a shower of organic material, which decomposes on the seafloor and depletes the dissolved oxygen at the sediment-water interface. For a modern reference, look up the oceanic dead zone in the northern Gulf of Mexico every fall season. These dead zones are often caused by harmful algal blooms. Eastward of the Appalachian Mobile Belt is the Caledonian Mobile Belt, which extends along the western border of Baltica and includes the present-day countries of Scotland, Ireland, and Norway. During the Middle Ordovician, subduction along the boundary between the Iapetus Plate and Baltica began. This formed a mirror image of the convergent boundary off of the east coast of Laurentia. This map shows the geographic locations of the Caledonides and the Acadian orogeny along the mobile belts of Laurentia, Avalonia, and Baltica. The Caledonides and Appalachians are mirror images of one another. The Acadian orogeny was the second Paleozoic orogeny to affect the Appalachian Mobile Belt. It began during the late Silurian and concluded at the end of the Devonian period. It affected a stretch of the Mobile Belt from Newfoundland in Canada to Pennsylvania in the United States. During this orogenic event, sedimentary rocks were folded and thrust up against the craton. As with the preceding Taconic orogeny, the Acadian orogeny occurred along an oceanic continental convergent boundary. As the southern Iapetus Ocean continued to close, the plate carrying Baltica collided with Laurentia, forming a continental-continental convergent plate boundary along the zone of collision. The antler orogeny in the Cordilleran Mobile Belt is somewhat of a mystery because there are no mountains left, but we know where they were. There are great volumes of clastic rocks deposited in Nevada and the surrounding region that range in age from late Devonian to mid-Pennsylvanian. Most mountain chains are associated with igneous intrusives or metamorphic basement rocks. The antler is an exception. What we do know of them comes from the study of the sediments they left behind as they weathered and eroded. You can see the location of the antler orogeny circled in red on this paleogeographic map. The antler actually lies slightly west of the Cordilleran Mobile Belt, so the possibility of a collision of a microcontinent or volcanic arc with the continental shelf is a good hypothesis for their formation. This is the end of Module 10, Part 1. In Part 2, we will discuss the biological evolution in the Devonian period.